Science isn't just facts, it's stories. Fluorine is the most aggressive element on the periodic table. Not kinda reactive. I mean, will steal your electrons and your lunch money. Its symbol F, atomic number 9. A pale yellow gas that looks harmless, which is how it wins. Fluorine is the most electronegative element. That means it pulls electrons harder than anything else. In chemistry terms, fluorine is an elite electron thief. If oxygen is reactive, fluorine is reactive with ambition. Fluorine almost never exists free in nature. Not because it's rare, because it bonds to things instantly. If you could bottle pure fluorine gas and open it near the wrong material, you might not like the results. It reacts with many substances violently, including things you'd normally consider stable. Even water isn't safe. Fluorine can react with water to form hydrofluoric acid plus oxygen plus heat. And hydrofluoric acid is one of the nastiest acids people regularly encounter. Not because it burns like a movie acid, but because it's sneaky. Most strong acids burn you by dumping hydrogen ions on your skin. Hydrofluoric acid is different. It penetrates deeper and binds with calcium and magnesium in your body. That's the terrifying part. It can cause deep tissue damage and mess with your heart rhythm by disrupting electrolytes. So yes, handle with extreme care. This is not a home chemistry experiment situation. Now for the big question, if fluorine is so dangerous, why do we use it? Because when fluorine bonds, it bonds like it's signing a lifelong contract. Carbon-fluorine bonds are some of the strongest in organic chemistry. That stability is incredibly useful. This is why fluorine shows up all over modern life. Not as fluorine gas, but locked inside stable compounds. An example is Teflon. That slick non-stick coating is a polymer called PTFE, packed with carbon-fluorine bonds. Those bonds make it resistant to heat and chemical attack. That's why it doesn't react with your food like a chaotic frying pan gremlin. Fluorine is also huge in pharmaceuticals. A lot of modern drugs include fluorine atoms. Why? Because adding fluorine can change how a drug behaves, its stability, how it dissolves, how long it lasts in the body, and how tightly it binds to targets. It's like tuning a molecule with a tiny chemical knob. A very powerful knob. Fluoride is another major player. That's fluorine with an extra electron, so it carries a negative charge. Fluoride shows up in toothpaste and sometimes in community water supplies because it can help strengthen tooth enamel. Enamel is mostly hydroxyapatite, a calcium phosphate mineral. Fluoride can swap in and form fluorapatite, which is more resistant to acid attack from bacteria. That's the practical story. It helps reduce cavities. Not magic, mineral chemistry. But dosage matters. Too much fluoride during tooth development can cause dental fluorosis, which changes enamel appearance. So it's a right tool, right amount situation. Like most things that actually work in the real world. Fluorine also matters in nuclear technology. Uranium enrichment often involves uranium hexafluoride, UF6. UF6 is weird because it's a solid at room temperature, but becomes a gas at relatively low temperatures. And that gas behavior is useful for separating isotopes. So fluorine is involved in some of the most advanced industrial processes on Earth, which is hilarious because it's also in your toothpaste. Here's another wild thing. Fluorine makes inert gases not inert anymore. Xenon, for example, can form xenon fluorides. That's a big deal historically because noble gases were once thought to be completely non-reactive. Fluorine helped prove chemistry always has loopholes. Fluorine is part of the halogen family. That includes chlorine, bromine, iodine, and astatine. Halogens are reactive because they're one electron away from a full outer shell. They want that last electron badly. Fluorine wants it the most. Because it's small, has strong nuclear charge pulling on electrons, and it doesn't mess around. That's also why fluorine forms strong hydrogen bonds in certain contexts, and why fluorinated compounds can have weird physical properties. Some fluorinated gases have been used as refrigerants. But environmental impacts matter. Certain classes can be strong greenhouse gases, and regulations have shifted usage over time. So fluorine chemistry is powerful, but not free. Every benefit comes with a trade-off you have to engineer around. If oxygen is the element of life, fluorine is the element of control. Lock it into the right compound, and it becomes incredibly useful. Leave it loose, and it becomes a chemistry horror story. The periodic table's smallest menace. Next up after fluorine is neon. And neon is basically the chill roommate after fluorine sets the kitchen on fire.